I want you to picture a very specific scenario for a moment.
Yeah.
You're sitting at your kitchen table.
Okay, setting the scene. I like it.
Yeah. So it's a Tuesday night, raining outside, and you are locked in a fiercely competitive game of Scrabble with your mom.
Oh, Scrabble is dangerous territory in my family.
Right. It gets intense. So you can see this utterly smug look on her face as she places a tile down for a triple word score.
Naturally.
You can read the slight lean in her posture, and you just look her dead in the eye and groan. The warmth, the eye contact, all those like microscopic human cues that tell you you're sharing a moment, they are all happening right there in your kitchen.
Okay, I'm with you so far.
But here's the catch. The person you are playing with lives 3,000 miles away.
Wow.
And you are experiencing all of this through a pair of glasses that look, almost indistinguishable from the frames you might be wearing right now.
It sounds entirely fabricated, honestly, like one of those concept videos a tech company would put out in the early 2000s that never, actually materializes.
It really does. But the architecture for that exact Tuesday night isn't theoretical anymore.
Right.
It's actively being built, and the prototypes are already functioning.
Which is just wild to wrap your head around.
It is. So we are unpacking a massive, in-depth conversation today between creator Cleo Abram and Meta CEO Mark Zuckerberg. And we aren't here to just do a surface-level gloss of a product launch.
No, we really need to get into the weeds on this one.
Exactly. Our mission today is to extract the literal roadmap of a future that represents one of the largest financial and infrastructural gambles in human history.
That is not an overstatement at all. The stakes are massive.
They really are. So we're going to tear down the physical mechanics of how these glasses actually bend light into holograms without being a clunky helmet.
Which is a physics nightmare, by the way.
We're going to get into that.
Yeah.
We also need to dissect the psychological holy grail of this entire endeavor achieving genuine human social presence.
Yeah, that's the whole reason they are building it.
Right. Then we have to look at the fragility of the human brain, how developers are trying to trick it without breaking the illusion. And finally, we are going deep into the cognitive side.
The AI piece.
Yep. We have to figure out if integrating artificial intelligence into our literal field of view removes our necessary human struggles, or if it just, forces us to build entirely different, higher-level intellectual muscles.
The stakes here are fascinating because we are talking about fundamentally altering the context of how computing happens over the next 2 decades.
Okay, let's unpack this. Let's start with the hardware.
Yeah.
Because before we can debate the societal ripples of holographic Scrabble, we have to understand how you physically project a digital human into a physical kitchen.
Right, the actual nuts and bolts of it.
The prototype discussed at length in the source material is called Orion. And what strikes me immediately is that this represents 10 years of research and development just to get a functioning alpha unit.
10 years. Just to get to the starting line, basically.
Yeah. And the core differentiator, the thing that makes this a completely different paradigm from virtual reality, is that these are transparent glasses.
That is the key distinction.
They are not opaque headsets blocking out your living room.
Yeah, a VR headset is relatively straightforward from an optics perspective. You take a high-resolution screen, you put it a couple of inches from the user's face, and use a magnifying lens so their eyes can focus on it.
Because you're basically replacing reality.
Exactly. But with augmented reality, layering a digital object onto the physical world in a sleek form factor, you run into a massive physics problem.
Right, because you can't just slap a tiny TV screen in a pair of clear glasses.
You really can't. You cannot put a traditional pixelated display in clear glasses without obstructing the real world.
Because if you put a tiny screen in the lens, I just have a tiny TV screen blocking my view of the kitchen table. And my eye can't focus on something a millimeter from my cornea anyway.
It would just be a blurry mess blocking your vision, so they had to abandon the concept of a screen entirely.
Which is mind-blowing.
It is. The source material breaks down how they replace traditional displays with a waveguide system.
I want to spend a minute on waveguides, because this is where the engineering sounds almost like magic to me.
It kind of is magic, or at least very advanced physics.
Right. So a waveguide isn't a screen. It's essentially a highly engineered, specialized piece of glass designed to channel light internally.
Yep.
Hidden inside the thick frames of these Orion glasses are microscopic projectors. Those microprojectors shoot light directly into the edge of the lens itself.
And that light needs to travel through the glass without leaking out. It bounces off the internal boundaries of the lens.
Like a hall of mirrors.
Kind of. It relies on a principle called total internal reflection.
Right.
It's very similar to how a fiber optic cable keeps light trapped inside it as it bends around corners.
Okay, that makes sense. But trapping the light is only half the battle, right?
Exactly. You eventually need that light to exit the glass and hit the user's eye to form an image.
And that is where these nano-etchings come in. The surface of these waveguides is covered in microscopic, nanometer-scale etchings.
Which are invisible to the naked eye?
Right. So if we think about the light bouncing around inside the glass, like a stone skipping across a pond, those nano-etchings act like perfectly angled ramps, placed exactly where the stone hits the water.
That is a great analogy.
When the light hits an etching, it breaks that total internal reflection. It redirects the light precisely out of the glass and directly onto your retina.
And because those etchings can control the exact angle the light enters your eye, your brain doesn't perceive the light as originating from the glass right in front of you.
Wait, really? So it fools your depth perception?
Completely. Your visual cortex processes the geometry of the light rays and perceives a three-dimensional hologram existing at a specific depth out in the real world.
So it's literal microscopic light manipulation. But I mean, the optical illusion is useless if the glasses don't understand the physical room you're in.
Right, because otherwise the hologram just floats around aimlessly.
Exactly. If my mom's hologram is going to sit at the kitchen table, the glasses need to know exactly where the surface of the table is. Otherwise, she's floating midair or like clipping through the wood.
Which means the frames of the glasses, alongside these microprojectors, have to house an incredibly dense array of sensors.
They have to map everything.
Yeah, environmental cameras are constantly running real-time 3D spatial mapping of your surroundings. But just as crucially, there are eye-tracking cameras pointed inward at you.
Because if the system doesn't know exactly where my pupils are darting, it can't render the hologram accurately in my field of view.
Precisely.
The source mentions they actually embed tiny lights into the frames to illuminate your eyes. That ensures the cameras can track your exact pupil movements in any lighting condition.
And they need to track your pupils for a concept called foveated rendering. Have you heard of that?
I have, but let's explain it for everyone listening because it's a huge part of how this works.
So, the human eye only sees in sharp detail in the very center of its vision, the fovea. Everything in your peripheral vision is actually quite blurry.
Even if we don't realize it.
Right, your brain just fills in the gaps to make you think you see everything sharply. By knowing exactly where you were looking, the glasses can dedicate all their computing power to rendering the hologram sharply right where your focus is.
And then they just drop the resolution everywhere else.
Exactly. They drop the resolution in your periphery to save battery and processing power.
It's a brilliant hack of human biology. But even with foveated rendering, the sheer amount of math required to run spatial mapping, eye tracking, microprojectors, microphones, and speakers simultaneously is enormous.
It is a massive computational load.
You simply cannot fit the processing power of a high-end desktop computer into a sleek pair of glasses without it catching fire on your face.
Physics creates a hard boundary there. Heat dissipation and battery size are the ultimate bottlenecks for wearable tech.
You don't want a hot battery pressed against your temple.
No, you definitely don't. The solution presented for the Orion Prototype is off-board compute. The glasses themselves don't do the heavy mathematical lifting.
So they outsource the brain.
Exactly. They house a specialized wireless radio that communicates with a separate computing device, essentially a dense little puck you keep in your pocket.
The puck takes the raw sensor data from the glasses, calculates the physics, the rendering, the AI processing, and then beams the finished visual data back to the glasses.
Which sounds simple in theory, but is incredibly hard in practice.
Right, because to do that without the user noticing a delay requires a wireless connection that acts almost like a high-speed invisible tether.
The speed is critical here.
If you're playing Scrabble and you move your head, the puck has to recalculate the perspective of the entire board and beam it back to your retina in less time than it takes your brain to process the head movement.
And if it fails to do that, even by a tiny fraction of a second, you experience severe motion sickness.
Oh, right, because your eyes and your inner ear get out of sync.
Exactly. The latency threshold is incredibly unforgiving. And we haven't even touched on how you actually interact with this digital board.
That's a good point. If you don't have a touchscreen or a mouse, how do you pick up a digital Scrabble tile?
You could use voice commands, but talking to yourself in public is weird.
Or wave your hands in the air for the cameras to see. But again, socially awkward. You look like you're swatting invisible flies.
Right. So the source outlines a fascinating, almost telepathic input method. It's a wrist-based neural interface.
This sounds completely sci-fi.
It intercepts the electrical signals your brain sends to your hand. When you decide to pinch your fingers together to pick up a digital tile, your motor cortex fires a signal down your arm.
Before your hand even moves.
Exactly. An armband or watch reads that electromyographic or EMG signal as it passes through your wrist before your fingers actually complete the physical motion.
So it literally decodes your intention.
Yes. And over time, you wouldn't even need to make the full physical gesture.
Wait, you wouldn't have to move your hand at all?
The system becomes sensitive enough that a microscopic muscle twitch, or eventually just the neural impulse of intending to type or click, is registered.
That is insane. So you could be sitting on a crowded subway with your hands completely still in your pockets, mentally typing out a text message that you see floating in the air in front of you.
That level of seamless integration is the end state goal. But it's clear from the analysis that we aren't all going to wake up tomorrow and swap our smartphones for premium 70-degree field of view holographic marvels.
Yeah, that Orion Prototype cost like $10,000 just to manufacture one right now.
Right. There is a multi-tiered product ecosystem being built to walk consumers up this technology curve.
Because you can't force a massive paradigm shift on a billion people overnight. You have to introduce the behaviors gradually.
You have to train the market. The foundational tier of this ecosystem is the displayless glasses, like the current generation of Ray-Ban Metas.
They look exactly like standard sunglasses.
Yeah.
There are no waveguides, no holograms.
But they house cameras, microphones, and speakers. They act as an ambient audio interface with AI.
So they normalize the behavior of wearing a smart device on your face. You can ask an AI what you're looking at, and it whispers the answer in your ear.
Exactly. It gets people used to the form factor. The next tier up introduces visual elements, heads-up displays, or HUDs.
HUDs are a middle ground, right? They don't have the wide field of view required to put a life-size person in your living room.
Yeah, they might only have a 20 to 30-degree field of view. It's essentially a small digital square floating right in front of you.
But that small square solves a major friction point with audio-only AI.
Which is human reading speed. We can read significantly faster than we can listen.
Oh, totally. If I ask a complex question, waiting for an AI voice to slowly read out a paragraph of text is agonizing.
Right, you just want to scan it. Seeing the text instantly populated in a HUD feels much more fluid.
Then you reach the third tier, the full holographic AR, the Orion prototypes we've been discussing.
And running parallel to all of this is a fourth category, mixed reality headsets, like the Quest line.
Because headsets are bulky, they aren't bound by those severe thermal and battery constraints of glasses.
Exactly. They can pack in vast amounts of compute power and high-resolution, opaque screens to offer immersive, full-room experiences today. They serve as the development ground while the glasses technology matures.
I look at this progression from audio glasses to HUDs to full AR, and the skeptical part of my brain just flares up.
What's the hesitation?
Are we really solving a problem here, or are we just taking the smartphone, a device that has already fractured our attention and isolated us, and strapping it permanently to our faces?
It's a very valid fear.
I mean, why is the tech industry so desperate to move computing away from the phone in our pocket?
What's fascinating here is if we look at the historical progression of computing, every major leap has been defined by a change in context.
Okay, walk me through that.
The desktop computer tied you to a physical location. Computing happened at a desk. Then the mobile phone unchained you from the desk, giving you the internet everywhere.
Right. The world became the office.
And that didn't just shrink the screen, it birthed entirely new behaviors, ride-sharing, mobile banking, augmented reality filters that fundamentally required mobility.
Because the computer was suddenly moving through the world with us.
But the smartphone still operates on a paradigm of distraction. It demands you divert your attention.
You have to look away from reality to use it.
Exactly. You are either present in your physical environment, or you are looking down at a glass rectangle in your palm. The philosophical drive behind AR is a shift toward contextual and social computing.
Meaning what, exactly?
The goal is to merge the digital seamlessly into your physical line of sight, so accessing technology doesn't require abandoning your physical presence.
Okay, so if I'm walking through an unfamiliar city using maps on my phone, My head is down. I'm bumping into people. I'm detached from the architecture around me.
Right, you're missing the city.
But with AR, the directional arrows are painted directly onto the sidewalk in my field of view. My head is up. I am present in the city, but still guided by the computer.
Exactly. But applying that to maps is the utilitarian use case. The emotional core of this, and the reason billions of dollars are being poured into this specific problem, is applying that heads-up paradigm to human interaction.
Which brings us to a massive tension in the source material. Having a perfect hologram of an arrow on the sidewalk is one thing, but having a perfect hologram of a human being in your house is the ultimate objective.
And that is a vastly more complex problem to solve.
We need to explore this concept of social presence. Because if you look at how human beings have communicated over long distances, it's a story of slowly clawing back the bandwidth we lose when we aren't physically in the same room.
Yeah, think about the progression. The telegraph gave us raw information, but stripped away tone and nuance.
Just words on a page.
Then the telephone gave us voice and inflection, which restored a massive amount of emotional bandwidth. And eventually, video calls gave us faces, allowing us to read expressions.
But a video call is still fundamentally a picture in a frame. You are consciously aware that you are looking at a flat representation of someone who is somewhere else.
You never forget the screen is there.
Right. So the definition of social presence, as outlined in this framework, is the visceral neurological sensation that you are physically sharing a defined three-dimensional space with another entity.
It is bypassing the logical part of your brain that knows they are 3,000 miles away.
And tricking your subconscious spatial awareness into believing they're occupying the air across from you.
And the urgency to engineer the sensation is driven by a profound societal crisis.
The loneliness epidemic.
Yes. The source material brings in some incredibly stark data to provide context for this technological push. We are living through an unprecedented epidemic of isolation.
The numbers they cite are genuinely jarring. If you look at the American Time Use Survey over the last 2 decades, the amount of time American adults spend socializing in person has dropped by nearly 30%.
Which is a massive cultural shift on its own.
But if you isolate the data for teenagers and young adults ages 15 to 24, that drop in face-to-face socialization is nearly 70%.
It is a systemic collapse of physical community. It's staggering.
And it culminates in this heartbreaking statistic. 15 years ago, the share of Americans who reported having absolutely zero close friends was around 3%.
And today?
Today, it has jumped to 12%. That is millions of people operating with zero foundational social support.
When presented with that data, the reflexive cultural narrative is to blame the technology we just discussed.
Oh, absolutely. We assume digital socialization, the smartphone, social media, is the direct cause of this isolation.
We view the screen as the replacement for the coffee shop.
I think most people intuitively feel that way. We assume teenagers aren't hanging out in person because they are addicted to scrolling TikTok in their bedrooms.
Right. But the analysis and the conversation forces a re-examination of causality. Is the digital socialization causing the isolation? Or are people claiming to digital socialization because the physical logistical capabilities of modern life have fractured?
That is such an important distinction.
The broader socioeconomic context is vital here. We have seen massive shifts in how communities are structured.
People are far more likely to move away from their hometowns and extended families for employment.
Exactly. The rising cost of living necessitates longer working hours and multiple jobs. Crucially, the third places, the civic organizations, local clubs, and accessible public spaces where casual socialization happens, have severely declined.
So the argument being made is that there is a massive unmet demand for socialization. People haven't decided they don't want friends.
No, the desire is still there.
But if your best friend had to move to another state for a job, and you work 50 hours a week, the friction of physical logistics makes maintaining that deep connection incredibly difficult.
So you turn to the phone because the physical reality is currently inaccessible.
This frames the development of AR not as an attempt to replace local physical interaction, but as a tool to bridge the gap created by these socioeconomic realities.
The stated goal isn't to build a device that stops you from walking next door to see a neighbor.
Right. If you can share a physical coffee with someone, you should.
The goal is to unlock the sensation of presence with the people you already cannot see physically.
It's about recovering the lost bandwidth of long-distance relationships. If you think about the current stopgap, the video call is fundamentally exhausting.
Oh, Zoom fatigue is very real.
I know you, the listener, have experienced this. You finish an hour-long Zoom call, and you feel entirely drained in a way that an hour-long coffee date doesn't drain you.
That exhaustion is cognitive load. In a physical room, your brain processes subtle cues effortlessly.
You know who is about to speak based on a micro shift in their posture.
Exactly. You have spatial audio, you hear a voice coming from a specific chair. On a video call, spatial audio is flattened.
And eye contact is literally impossible because the camera is offset from the screen.
Your brain is burning massive amounts of energy trying to compensate for missing sensory data. It's constantly scanning a 2D grid of faces to piece together the rhythm of a conversation.
So, social presence aims to eliminate that cognitive drain. If the glasses can accurately render your friend in your physical space, complete with spatial audio and accurate eye contact tracking, the micro-interactions happen naturally again.
Your subconscious takes over the heavy lifting.
But achieving that subconscious buy-in brings us to a massive hurdle. Creating reality is incredibly difficult, but the human brain is so finely tuned that breaking reality is shockingly easy.
The human brain is the ultimate anomaly detector.
What do you mean by that?
Well, over millions of years of evolution, we developed an incredibly sensitive mechanism for identifying when something in our environment isn't quite right.
Like a rustle in the bushes.
Right, or an object moving unnaturally. It kept us alive. When developers are trying to design presence, they are delivering a highly targeted illusion directly to that anomaly detector.
And the margin for error is essentially zero. The source discusses how you don't just need one killer feature to create presence, you need dozens of complex systems to function flawlessly in unison.
If even one system falters for a millisecond, the illusion shatters. Your brain instantly reverts to recognizing it's looking at a computer graphic.
The field of view limitation we discussed earlier is a prime example of an illusion breaker.
It's a huge one.
If an incredibly lifelike hologram of a person is standing in your room and you turn your head slightly, but the glasses only have a 30-degree field of view,
The hologram will simply clip out of existence at the edge of the lens. Half their body vanishes.
and the spatial illusion is instantly destroyed. Latency is an even more visceral breaker, though.
Oh, latency is a killer. Human interaction is built on immediate physical physics.
Right. If I reach out to hand a digital object to a hologram, and there is a 50 millisecond delay between my hand moving and their hand receiving it, my brain flags the lag.
The biological threshold for perceiving delay is incredibly low.
Furthermore, the virtual physics engine must perfectly mirror physical reality.
Yeah, if a digital ball rolls off a digital table onto your physical floor, the software has to calculate the exact trajectory based on the height of the physical table and the gravity of the room.
And render the bounce perfectly. If it floats for a microsecond too long, the brain rejects it.
But when developers actually manage to dial all of those elements in, the latency, the physics, the spatial mapping, the results are wild.
There's an anecdote in the interview about a mixed reality ping pong demo that perfectly illustrates this threshold of presence.
It's a brilliant case study in spatial awareness overriding cognitive logic.
Okay, so a user puts on a headset and holds a physical controller that represents their ping pong paddle. They are in a digital room, standing at a digital ping pong table, playing against a digital opponent.
And the development team had managed to eliminate the latency and dial in the physics engine so perfectly that the ball bounced exactly as the brain expected it to.
So the user played the game for several minutes. Their subconscious entirely mapped the dimensions of the virtual table as a solid physical object in their environment.
Which is exactly what you want the brain to do.
Right. So the game finishes, and the user instinctively goes to set their paddle down on the ping pong table.
Except, obviously, the table doesn't exist.
Exactly. It's just light being beamed into their eyes. They let go of the controller in midair, fully expecting it to rest on the surface, and the controller plummets to the hardwood floor and shatters.
Which is a bummer for the hardware budget, but it's the ultimate compliment to the engineering team.
Seriously. The illusion was so airtight that the user's brain completely discarded the conscious knowledge that they were standing in an empty room.
But getting the spatial physics right is one thing. When you introduce digital human beings into that space, you run headfirst into a massive psychological barrier known as the uncanny valley.
The uncanny valley is fascinating. It's a well-documented phenomenon in robotics and computer graphics.
Yes. As a representation of a human becomes more realistic, our empathy and comfort with it increase.
Okay, but point.
Exactly, up to a point. Right before it becomes perfectly photorealistic, When it looks 95% human, but the skin texture is slightly plasticky or the eye movements lack those tiny microsaccades, our emotional response plummets.
We feel a deep sense of revulsion. It triggers an evolutionary alarm.
It looks like a corpse or something diseased. It looks fundamentally wrong.
So Meta has to figure out how to represent you holographically without triggering that revulsion. The source details their two-track approach for this.
Developing hyper-realistic Kodak avatars, which use massive neural networks to render your exact pores and lighting.
And simultaneously developing highly expressive, stylized, cartoon-like avatars.
And the psychological findings on what creates a sense of presence with these avatars are entirely counterintuitive.
You might assume that to feel like you're sharing a space with a friend, their avatar must be perfectly photorealistic.
Right. But the brain is actually highly adaptable to aesthetic context. If you place a photorealistic avatar into a stylized video game-like environment, the brain accepts the discrepancy.
Like watching a live-action actor walk through an animated movie, we can process that.
Exactly. But the breakthrough finding is that the reverse is also true. You can project a heavily stylized cartoon avatar of your friend into your perfectly photorealistic physical living room.
And your brain will still accept them as a valid, deeply felt social presence.
Yes. But there is a massive caveat to that. The brain doesn't just accept any cartoon.
The condition for acceptance is behavioral authenticity. The cartoon avatar must perfectly mirror the authentic physical mannerisms of the user in real time.
This is such a profound insight into human psychology. The realization is that mannerisms matter vastly more than pixels.
So if an avatar has the exact skin texture and eye color of my best friend, but stands perfectly still with generic, robotic, idle animations,
your brain rejects it as an imposter.
But if it's a cartoon character with a giant head, yet it tilts its head at the exact angle my friend does, shrugs with the exact cadence, and blinks at the same rhythm,
your brain instantly says, I know who is inside that. It speaks to how we biologically identify each other.
we are hardwired to recognize movement signatures.
It's a concept called biological motion perception. You can recognize a family member from 100 yards away just by the rhythm of their gait.
So by capturing the real-time telemetry of the user's face and body and mapping it perfectly to the avatar, they bypass the uncanny valley entirely by delivering the soul of the movement.
Even if the shell is stylized.
Okay, so visual and auditory presence are incredibly complex, but we have a clear roadmap to solving them. But as a host in the interview points out with a very simple, poignant observation, there is a fundamental human limitation to this entire enterprise.
The physical touch aspect.
She states, "I miss hugging my mom." And that brings us to the final frontier of virtual interaction, the tactile world, haptics and smell.
If visual and auditory systems are moving at light speed, tactile feedback is barely crawling out of the primordial soup.
It's that far behind.
Oh, absolutely. To understand why it's so difficult to simulate touch, the transcript references the concept of the sensory homunculus.
I remember this from high school biology. The homunculus is a distorted map of the human body, right?
Yes. If you drew a person where the size of their body parts corresponded directly to how much processing power the brain dedicated to sensing touch in those areas, it looks like a monster.
It has a massive face, giant lips, an enormous tongue, and absolutely gargantuan hands, while the arms, torso, and legs are tiny.
Our sensory perception of the physical world is incredibly dense in our hands, which is why all haptic development starts there.
We are already seeing localized vibration haptics. Like in that ping pong demo, the controller uses high-definition actuators to create a sharp, localized vibration in your palm.
It mimics the exact physical frequency of a hollow plastic ball hitting a wooden paddle. It tricks the nerve endings in your hand.
Localized vibration is excellent for simulating impact. But true tactile presence, the feeling of hugging someone or grappling in jiu-jitsu, as mentioned in the interview, requires force feedback.
Let's clearly define the mechanics of force feedback, because it's vastly different from a controller just vibrating.
Right, a vibration just tells your skin an event occurred.
Force feedback physically intercepts and opposes your biomechanics.
Okay, so if you are grappling with a digital opponent and you try to pull your arm away, but the digital opponent has a grip on your wrist,
a physical device must actively exert motorized force against your actual muscles, restricting your real-world movement to match the digital physics.
To do that across the entire body, you aren't talking about a wearable watch. You are talking about a full-body exoskeleton strapped to your limbs.
Packed with motors capable of instantaneously matching human torque without snapping your bones. It is an engineering nightmare of weight, power delivery, and safety.
So force feedback at that scale is decades away from being a consumer-friendly living room reality.
Easily decades. And then there is the simulation of smell, which is disproportionately tied to memory and emotional resonance in the human brain.
The smell of your mom's kitchen, the exact scent of rain on asphalt.
Delivering synthetic chemical compounds safely and accurately to the olfactory system in a split second, and then clearing that scent away instantly so it doesn't linger and ruin the next digital environment.
That sounds impossible.
It is a problem we aren't even close to solving on a consumer device level.
So the profound takeaway here is that while we will achieve a startlingly realistic visual and auditory ghost of the people we love, the full sensory reality, the grounded weight of physical connection, will remain exclusively the domain of the physical world for a very long time.
Which I think is a good thing, honestly.
There's an undeniable comfort in that reality. The physical world retains a monopoly on actual warmth.
Exactly.
But having a perfect responsive hologram of your friend standing in front of you doesn't mean much if the software running the glasses fundamentally changes how you interact with them.
And that brings us to the second half of this massive equation.
We've covered the hardware, the spatial presence, the visuals. Now we must dive into the cognitive half, artificial intelligence.
This is the shift from the mechanics of seeing the digital world to the philosophy of thinking in it.
Because the glasses aren't just projecting holograms. They are constantly interpreting the world through an integrated AI.
And the central tension in the source material revolves around a critical philosophical debate.
As we integrate AI into every waking moment of our lives, does it remove our humanity or enhance it?
Will having an omniscient intelligence whispering in our ear make us intellectually lazy, or will it elevate our capabilities?
To navigate this, the host introduces a brilliant framework. She divides human effort into a spectrum of struggle.
This framework is essential for cutting through the hype of AI. On one side of the spectrum, you have friction.
These are struggles that are purely obstacles. They don't build character, they don't impart deep wisdom, they just block progress and connection.
The perfect example of this, drawn directly from the text, is the language barrier.
Oh, absolutely. If you travel to a foreign country, struggling for 20 minutes to mime your way into finding a hospital or ordering a meal isn't a beautiful character-building exercise in rigorous thought.
No, it's simply a logistical barrier that prevents human empathy and understanding.
And this is an area where the complete elimination of friction by AI is an unalloyed good. The interview highlights that the current Ray-Ban Metas have already achieved a form of the Star Trek Universal Translator.
Which is incredible to think about. You can be standing in front of someone speaking Spanish, the glasses capture the audio, the AI processes the translation, and whispers the English translation into your ear with almost zero latency.
It instantly evaporates a barrier that has divided human cultures for millennia. That is friction removal at its absolute finest.
But then we have to slide to the other end of the spectrum, to the struggles that build human muscle.
These are the struggles where the difficulty isn't a bug, it's the feature.
Right. The effort required to overcome the struggle is the mechanism that builds cognitive capacity, emotional intelligence, and critical reasoning.
The host poses a challenging hypothetical based on this. If the AI in your glasses is monitoring your biological signs and analyzing your conversation, and it prompts you on your HUD, hey, your tone is aggressive, you seem angry, you should probably apologize and say XYZ to your partner.
That might solve the immediate argument, but if we outsource our emotional regulation to an algorithm, do we lose the vital human muscle of introspection?
Do we forget how to independently identify and articulate our own feelings?
That emotional outsourcing is a deep concern, but the transcript focuses heavily on a more immediate technical battleground for this concept.
The process of learning to code. This is the perfect crucible for the debate.
It really is.
If generative AI can write a flawless, complex software application in 30 seconds, why should a single high school student ever be forced to struggle through learning Python?
If we connect this to the bigger picture, to understand the answer, we have to contextualize how the struggle of coding has already evolved.
A generation ago, programming was a brutal struggle against the machine itself.
You were dealing with low-level languages, writing machine code, manually allocating memory. The friction was immense.
Then we developed higher-level languages that abstracted away the hardware. It removed friction, but developers were still fundamentally writing syntax.
And now, generative AI is about to abstract away the syntax entirely. In the near future, children won't write lines of code. They will use natural language.
They will describe a concept. I want a physics-based puzzle game where you use gravity to guide water into a bucket.
And the AI will generate the entire application instantly.
So the question remains, if the machine generates the product, does the child's intellectual muscle atrophy? Do they stop struggling entirely?
The compelling argument made in the source is that human beings don't stop struggling. The nature of the struggle simply shifts up the stack.
The child is no longer struggling to remember where to place a semicolon.
Instead, they are struggling with higher-level creative architecture.
The AI builds the water game, but the game is boring. Now the child have to grapple with deeper questions.
Why isn't this engaging? How do I refine the physics variables to make it challenging? How do I structure a narrative progression that keeps a player hooked?
The struggle moves from the manual labor of syntax production to the intellectual labor of creative direction and iteration.
But even acknowledging that shift, the source takes a firm stance that we absolutely must continue teaching basic coding and mathematics.
And they use the calculator analogy to explain why. It's a historically grounded analogy, isn't it?
It is. When pocket calculators entered classrooms, there was widespread panic that an entire generation would lose the ability to do basic math.
The fear was that the muscle would entirely atrophy. And it's true that most adults today couldn't do complex long division by hand if their life depended on it.
Yet we still mandate that every child learns basic numeracy. We teach it because understanding the mechanics of math is crucial, even if a machine does the execution.
If you don't have an intuitive sense of how numbers scale or how percentages work, you cannot tell when the calculator spits out a wildly incorrect answer due to a typo.
You need that foundational understanding to navigate interest rates, critically evaluate statistics in the news, and understand the shape of the world.
The exact same logic applies to AI and coding. We don't teach students to code today because the world desperately needs more people to manually type out Python syntax.
We teach them to code because it is a premier vehicle for teaching rigorous thinking.
Let's define rigorous thinking for the listener.
Rigorous thinking is the ability to break down a massive, ambiguous problem into a logical sequence of discrete, solvable steps.
It's understanding inputs, outputs, edge cases, and systemic logic flows. It is the grammar of logic.
Even if the AI is writing the essay or generating the software, you need rigorous thinking to know if the underlying logic of the AI's output is actually sound.
I want to ask everyone listening to this right now to think about your own job, your own daily tasks. How much of what you do every day is just syntax?
Filling out forms, reformatting data, writing boilerplate emails.
Exactly. And how much of it is actual rigorous thinking? The promise of AI is to automate the syntax of your job so you can focus entirely on the rigorous thought.
But that promise relies on a very specific view of human nature.
And this is where I have to push back against the inherent optimism of the source material.
I was wondering when you'd bring this up.
The tech industry assumes that if you remove the low-level friction, humans will naturally, inevitably seek out the higher-level struggle. They assume we all want to climb the intellectual mountain.
Which is a big assumption.
But if we build an intellectual couch, if we make it incredibly easy to generate a passable app, a passable essay, a passable strategic plan with zero effort, won't a massive percentage of the population just sit on the couch?
It's a critical vulnerability in the utopian vision. Are we fundamentally driven to climb the mountain, or are we biologically hardwired to conserve energy and accept the baseline output because it's good enough?
If a student can pass a class by accepting the first draft an AI generates, will they ever subject themselves to the painful, rigorous struggle of refining and editing?
Historical precedent suggests that humans generally use new tools to raise the baseline of complexity.
Like with word processors.
Yeah. When word processors eliminated the physical struggle of retyping entire drafts on a typewriter, people didn't stop writing. They started writing vastly more complex, heavily edited documents because the friction of a revision was gone.
However, the sheer frictionless ease of generative AI presents a temptation to coast that is unprecedented.
It will require a massive cultural and educational shift to intentionally value and reward the invisible struggle of rigorous thinking when the perfectly formatted, easy answer is available instantly.
And this debate isn't just happening in classrooms, it's reshaping the media we consume every single day.
We need to look at how these AI muscles are being flexed in the real world.
And critically, who owns the underlying systems powering them? Let's examine the immediate future of social media creators and the massive philosophical divide in how AI should be controlled.
The landscape of social media has already fractured from its original intent. It began as a utility for maintaining ties with your physical social graph.
Seeing vacation photos from friends and family.
Now, it is predominantly a broadcast medium. It's about consuming highly algorithmic content from professional creators.
And AI is acting as an accelerant to this shift in bizarre ways. On the consumer level, AI will be embedded into the glasses to automate the friction of sharing.
If you are wearing the glasses and experience something funny, you don't need to manually export the video, drop it into an editing timeline, cut the clips, and add text.
The onboard AI will recognize the highlight, instantly edit it into a culturally relevant meme format, and offer to send it to your group chat before you've even processed the moment.
But the implications for professional creators are far more radical. The transcript introduces the concept of AI artifacts, and this is where the lines of parasocial relationships get incredibly blurry.
Let's define the problem for a popular creator. You might have 5 million highly engaged fans who want to ask you questions, get your advice, or just feel connected to you.
As a human being constrained by biology and time, you can only interact with a fraction of a percent of them.
The demand for connection vastly outstrips the supply of your attention. So the proposed solution is for the creator to build an AI artifact.
You take an advanced AI model and train it extensively on your entire body of work, every podcast, every video, every article you've ever produced.
You train it on your specific tone of voice, your humor, and, crucially, your boundaries.
Defining exactly what topics the AI is allowed to discuss and what it must politely decline.
Once trained, you deploy this artifact to your audience. Millions of fans can have deep, personalized, real-time conversations with an entity that thinks and speaks remarkably like you 24 hours a day while you're asleep.
The immediate reaction to this is usually revulsion. It sounds dystopian.
It sounds like a deepfake trying to trick people into believing they are talking to a human.
But the expert in the interview is meticulous about defining the framing of this technology. The framing is everything.
This is not presented as an imposter. It is explicitly labeled and presented as an AI.
The analogy they use to contextualize it is that an AI artifact is like an interactive sculpture.
An interactive piece of art. If I read a book written by an author I admire, I'm interacting with a static artifact of their mind. The book can't answer my questions.
The AI artifact is simply the next evolution of that medium. It is an interactive, dynamic extension of the creator's knowledge base and brand built by the creator for the fans to explore.
But the ability for anyone to generate these highly persuasive interactive personas, to instantly generate code, to manipulate audio and video, it understandably terrifies people.
The power of these systems is scaling exponentially.
Which forces the single most important question in technology today. How do we keep this safe?
And the host in the interview confronts this head-on. She channels the public anxiety.
Shouldn't this immense power be locked down in a vault? Shouldn't access to advanced AI be heavily restricted and gated by a few responsible entities to prevent bad actors from unleashing chaos?
This is the battlefield for the soul of AI development. It is known as the open versus closed debate.
It is a fundamental ideological clash over the safest architecture for the future of humanity's intellectual infrastructure. Let's lay out the two opposing philosophies.
On the closed side, you have companies like OpenAI, Google, and Anthropic. Their thesis relies on centralized control.
The closed model envisions building an incredibly powerful, godlike AI system, but keeping the underlying code completely secret.
They host the model on their servers, and you, the user, can only interact with it through their specific portal.
You type a prompt into their website, and they decide if it's safe to give you the answer.
If a bad actor asks for instructions on building a bioweapon, the centralized system flags it and denies the request.
The security relies on a small group of highly vetted engineers constantly updating the guardrails. It's the fortress approach. Centralized control equals centralized safety.
Meta, however, is championing the exact opposite approach. They are advocating for a decentralized, open-source future.
Meta's vision is that there shouldn't be one single AI monolith controlled by a tech conglomerate in Silicon Valley.
They believe every small business, every hospital, every creator, and every individual should have their own distinct, localized AI models running on their own hardware.
Tailored to their specific values and needs. But to enable that, Meta's doing something incredibly controversial.
They are spending billions of dollars training these cutting-edge models like their Llama series.
And then simply giving the underlying blueprints, the weights and the code away for free on the internet. Anyone can download it and modify it.
And the immediate instinctual reaction from the public and politicians is, that is incredibly reckless.
If you open source the blueprints to advanced AI, you are handing a loaded weapon directly to criminal syndicates and hostile nation-states. You lose the ability to censor dangerous prompts.
So how does the expert in the transcript defend this as the safer path? They rely on a counterintuitive truth about software security that has been proven over decades of computer science.
Often summarized as Linus's law. Given enough eyeballs, all bugs are shallow.
Well, let's explain that dynamic. Why does exposing the code make it safer?
In a closed fortress model, only the 100 engineers working inside the company can examine the code to find vulnerabilities, biases, or dangerous failure modes.
But those 100 engineers have blind spots. If you open source the code to the entire world, yes, bad actors will inevitably try to find vulnerabilities to exploit.
But they are vastly outnumbered. Hundreds of thousands of well-intentioned developers, academic researchers, and cybersecurity experts will also be ripping that code apart.
The collective intelligence of the global community scrutinizing every line. The open source community will discover vulnerabilities, identify systemic biases, and patch security holes orders of magnitude faster than a closed team ever could.
We've seen this in practice with the rapid iteration of Meta's models. They released Llama 3 into the wild.
The global community immediately stress-tested it, broke it, found its limits, and within months, that feedback loop produced Llama 3.1.
And then 3.2, each iteration vastly more robust and secure than the last.
Let's make this abstract debate incredibly concrete. Imagine a scenario where a closed AI system is heavily programmed to refuse any prompt that sounds like medical advice because the corporate lawyers are terrified of liability.
A user in a rural area with no immediate access to a doctor describes a specific set of life-threatening symptoms, and the closed AI simply responds, "I'm sorry, I cannot provide medical advice."
The rigid safety guardrail actually causes harm through inaction. In an open source ecosystem, a global health organization could take that foundational Llama model, bypass the corporate liability filters, and fine-tune it specifically on vetted medical triage data.
Creating an accessible tool that can accurately guide that rural user to emergency care.
Open source allows the tool to be specialized for vital edge cases that a centralized monolith might legally refuse to touch.
But this entire vision, the open source proliferation, the AI artifacts, the seamless rendering of holographic realities, relies on one massive underlying assumption about the physics of computing.
And this brings us to the final, most staggering insight in the interview, the great bet.
This is the fulcrum upon which the entire tech industry is currently balancing. It's the question of scaling and whether the current trajectory of AI has a ceiling.
The transcript frames this around the concept of the asymptote. In mathematics, an asymptote is a line that a curve approaches infinitely but never actually reaches.
In the context of technology development, an asymptote is a plateau. It's the wall.
In previous eras of artificial intelligence research, developers would build a model, feed it more data, and give it more computing power, and the AI would get smarter.
But eventually, it always hit an asymptote. You could pump 1,000,000 times more data into it, and the model wouldn't improve.
The underlying architecture simply couldn't extract any more pattern recognition from the noise. It plateaued.
But the current generative AI explosion isn't built on those old architectures. It's built on something called transformer-based architectures.
And the wild, slightly terrifying truth revealed in the interview is that developers have not found the asymptote for transformers yet.
The defining characteristic of a transformer is its attention mechanism. Older models process data sequentially, one word at a time, forgetting the context of the first word by the time it reached the last.
Transformers look at an entire massive data set simultaneously. They map the complex, multidimensional relationships and context between every single data point at once.
Which means that when you feed a transformer more data, it doesn't just get overwhelmed. It uses that new data to build exponentially more complex webs of context.
Exactly. And because of that architecture, every single time they increase the amount of training data and increase the computing power, the model gets demonstrably, measurably smarter.
The curve is still pointing straight up. And the physical scale required to maintain that upward curve is difficult to comprehend.
The transcript notes that training the Llama 3 model required a cluster of roughly 20,000 GPUs.
GPUs being the highly specialized graphics processors required to perform the massive parallel mathematics of neural networks.
20,000 GPUs is already a staggering infrastructure feat, but for the upcoming Llama 4 model, they are building data centers housing over 100,000 GPUs.
And you have to understand, building a cluster of 100,000 GPUs isn't just a matter of buying them and plugging them into a wall.
The bottleneck becomes the fiber optic networking between the chips. To train a model, these 100,000 processors have to pass terabytes of weight adjustments back and forth to each other in nanoseconds.
You are essentially trying to build a single, perfectly synchronized, distributed supercomputer the size of multiple football stadiums.
The power requirements are astronomical. The cooling requirements demand entirely new civil engineering solutions.
We're talking about hundreds of billions of dollars in capital expenditure funneled into these massive AI factories.
It is arguably the single largest, most concentrated infrastructural bet in the history of corporate capitalism.
And the entire bet rests on that asymptote. What happens if they are wrong? What if the transformer architecture finally hits the wall next year?
What if they spend $50 billion building the 100,000 GPU data center for Llama 5, and it is only 2% smarter than Llama 4?
If they hit the asymptote, the explosive narrative of AI grinds to a halt. The dream of perfect, flawless, generative video, perfectly intelligent digital ghosts, and instantly rendered holographic realities gets delayed by decades.
Computer scientists would have to go back to the drawing board to invent a fundamentally new mathematical architecture. The bubble bursts.
But what if they are right? What if the architecture holds? What if they scale to 1 million GPUs and the model just keeps linearly expanding its capacity for reasoning and generation?
If there is no immediate wall, the next 20 years will be the most aggressively dynamic, fundamentally disruptive period of technological and societal change in human history.
The capabilities of these systems will rapidly outpace our biological ability to adapt our social structures to them.
It forces a total reevaluation of how we work, how we connect, and how we perceive reality itself.
So what does this all mean? We have dissected a massive amount of complex terrain today.
We covered a lot of ground.
We started by tearing down the literal mechanics of the future, how microscopic nanoetchings and waveguides trap and bend light to project three-dimensional holograms into our visual cortex.
Paving the way for transparent, contextual computing that finally allows us to look up from our screens.
We examine the profound, desperate societal need driving this hardware, the epidemic of human isolation, and the quest to engineer true social presence.
Tricking the brain's spatial awareness into feeling genuine connection across thousands of miles.
We walked the razor's edge of the uncanny valley, learning that the human brain prioritizes the authentic rhythm of a friend's mannerisms over perfectly rendered photorealistic pixels.
And we confronted the hard physical limits of haptic force feedback, recognizing that the warmth of a physical embrace cannot be digitized.
And we waded into the deep philosophical waters of the AI era, the vital necessity of protecting the human muscle of rigorous thought against the intoxicating convenience of automated friction.
We explored the high-stakes battle for an open-source ecosystem, relying on the collective scrutiny of the globe to secure our digital future.
All while waiting to see if the massive infrastructural bet on transformer architecture will finally hit a wall. It is entirely rational to feel a sense of vertigo when looking at the sheer scale and pace of this roadmap.
The change is definitely intimidating.
But as we navigate this transition, retreating into fear isn't a viable strategy. The takeaway for you navigating your career and your relationships right now is to aggressively maintain your curiosity.
Approach these emerging tools, whether it's an AI model automating your syntax today or a pair of holographic glasses tomorrow, not as replacements for your humanity,
but as powerful levers to elevate your rigorous thinking and deepen your connection to the people who matter most.
And to leave you with one final thread to pull on. If we assume the most aggressive timeline holds true,
okay, lay it on us.
If we eventually achieve a state where holographic AR provides flawless, instantaneous visual gratification and pervasive AI completely removes every ounce of cognitive friction, anticipating your needs before you even articulate them.
A completely fluid, frictionless digital existence.
Exactly. If our digital reality becomes that perfectly malleable and responsive to our whims, will the rigid, uneditable, relentlessly slow-moving nature of our physical reality begin to feel unbearably frustrating?
Oh, wow. When you take the glasses off, will the physical world feel broken simply because it resists us?
Will sitting at a physical table to play Scrabble feel agonizing because the wooden tiles don't magically tally their own points and instantly reset the board?
Will we lose our tolerance for the beautiful, stubborn friction of the real world? That is a massive question we will all have to answer for ourselves. A massive thank you to everyone for taking this journey with us today. Keep questioning the systems being built around you, maintain your rigorous thought, and we will see you on the next Deep Dive.